Oh, yeah, so I happen too. Because it's about, so you get. Yeah, it's really great. I don't even know. Well, I feel. No, that's such. Like. It's not sure now. The next week, yes. Oh, to just do this one. I'm gonna. It is. Why? I know. Yeah.
Okay, so page 13 through 18, I'm just going to pick out problems for us to work on, and then the rest you guys can finish for homework over the weekend to turn in on Monday. So Monday, you guys will turn in the packet, and I'll just look through looking for completion, and then I'll give you a homework grade for that. Okay, if you haven't put your phone up on the wall, if you guys can do that. So let's go to page 13, and let's see. We did A and B, so hopefully we're okay with that. I'll leave C for you guys to try on your own. Number 4, let me try one or two of these. This is solving trig equations and then using identities where necessary. So I'll go through. Yeah, let's try. Okay, let's try number 4, part A. So cosine squared x minus cosine x plus 1 equals sine squared x. It's a lot easier to solve a trig equation if I can get everything down to one trig function, either cosine or sine. So it looks like it's easiest to get the sine squared in terms of cosine. There's cosine squared and cosine, so there's two different cosine squared and cosine x. I think it's easier just to find the one thing that's that we can replace. So we think it's going to be easier to get that sine squared in terms of cosine. So one identity that we all should know is sine squared x plus cosine squared x equals 1. Okay. There are other identities that kind of build off of this one involving tangent and also one involving cosecant, secant. They all can be built off of this. So this is really the main one that we can that we all should know. So sine squared is equal to 1 minus cosine squared x. So then if I make that substitution, I can now get everything in terms of cosine and see if that will help us eventually solve for x. Okay, combine like terms, I'll bring everything over to one side. So I'll add cosine squared x to this side. So cosine squared plus cosine squared is 2 cosine squared. The 1 minus 1 is 0. That's nice. That's going to wipe this out. So there's no trinomial factoring. We can just worry about taking out the GCF. Our GCF is cosine of x. Set each piece equal to 0. So then we think about our unit circle values. Cosine of x equal to 0 when x is equal to pi over 2 and 3 pi over 2. And then cosine of x equals to 1/2. That's going to be in that pi over 3 family. And then we know cosine is positive in the first and the fourth quadrant. So pi over 3 and 5 pi over 3. Okay. Part B, we can bring everything over to one side, factor GCF out, and then solve. So I'll leave that for you guys to do on your own. This one, sine of x equals cosine of x minus 1, cosine 2x minus 1. There's a double angle identity here. We want to get this out of double angle form. So there's 3 variations of cosine 2x. You want to pick the one that will be the easiest to move forward. So we see there's sine involved here. So there's a cosine. There's double angle cosine expansion with just involving sine. So cosine of 2x is equal to 1 minus 2 sine squared x. So then we make that substitution and we get everything in terms of sine, bring everything over to one side, factor, and solve. So I have you guys try that a little bit later. Okay, page 14. Okay, 14, this one's a strange one here. Sine of 4x equals 1/2. We talked about yesterday how we can use inverse trig to kind of isolate that 4x. So if we isolate that 4x, inverse sine of 1/2. So inverse sine of 1/2, again, that's essentially saying this represents theta. We can ask ourselves, sine of what theta measure is equal to 1/2? What theta value will allow that trig ratio to be 1/2? So we know this is going to be in that pi over 6 family. So pi over 6, and we know sine is also positive in the second quadrant, so 5 pi over 6. The issue is that this is normally would be the solution, but the fact that we are setting that equal to 4x, all this is going to end up shrinking. So we want all of our solutions to land between 0 and 2 pi. So we may have to add a bit more coterminal angles, expand it out so that when we divide by 4x, when everything shrinks, we can have our full sets or our full set of x values that all land between 0 and 2 pi. So a little bit tedious here, just having to add 2 pi multiple times until eventually we have enough. So to get the coterminal angles, if I do pi over 6 plus 2 pi, that's the same thing as pi over 6 plus 12 pi over 6. So that's 13 pi over 6. And this one, coterminal angle, 5 pi over 6 plus 12 pi over 6, that's going to be 17 pi over 6. So there's going to be a couple of variations here. We're going to go all the way out to, once we get out to 13 pi over 6 and 17 pi over 6, if we keep adding 2 pi, we get 25 pi over 6, 29 pi over 6. This is way past 2 pi, but if you see what happens here, if we divide by 4, all these values are going to end up shrinking. So dividing by 1/4, sorry, dividing by 4 is the same thing as multiplied by 1/4. So pi over 6 times 1/4 is pi over 24, 5 pi over 24, 13 pi over 24. And it's actually good to go past 2 pi, because then we know that we've hit all of our, I'm sorry, this one's still too much. So I think I made the adjustment to say, let's just find x values between 0 and pi. So we know that we've gone past pi when we get something that is more than 1, right? So 25 pi over 24, that's more than 1. So, I mean, if we had to go from 0 to pi, we have to probably do a lot more. But once we see one that's past our interval, we know that we've reached, that we didn't end up skipping over any. Okay, let me do part E with you here as well. So cotangent squared minus cosecant of x is equal to 1. We want to use trig identity to get either cotangent in terms of cosecant or cosecant instead of in terms of cotangent. So there is another identity besides sine squared plus cosine squared equals 1, but we can build everything off of this identity that we all know. Okay. So if I start off with sine squared plus cosine squared equals 1, if I divide everything by either sine squared x or by cosine squared x, it will turn into another identity that we can use. So the one that can be associated with these will be the one that is involving dividing everything by sine squared. So let's see what happens. So sine squared over sine squared is 1. Cosine over sine is cotangent. And the 1 over sine is cosecant. So, you know, this identity, I really don't have it memorized. I just have this one memorized, and I know that I can always derive the other identities. So this one is helpful because we know that we have a substitution for cotangent squared. So if I can replace cotangent squared with cosecant squared x minus 1, now I have everything in terms of cosecant, and that can help me move forward. So cotangent squared x is cosecant squared x minus 1. So we can take this and substitute in for this. Okay, so we have cosecant squared x minus 1 minus cosecant of x equals 1. Okay, let's bring everything over to one side. Now this is going to be a trinomial factoring problem. You see how there's a squared, degree 1, and then there's a constant. So we can treat this like a factoring problem. So if you're comfortable, you can jump directly into factoring here. But if you want to do an easier version of this problem, you can start off with thinking, well, this is essentially the same as x squared minus x minus 2 equals 0. So if it helps, you can factor this out and then replace all your x's back with cosecant and then go from there. So we know multiplies to be -2, adds to be -1. That's going to be x minus 2 and x plus 1. Okay. So I've done the factoring with an easier problem. Now let's bring back the original variable, which is cosecant. Okay. We set both parentheses equal to 0. Cosecant of x equals 2 and cosecant of x equals -1. I like to think in terms of sine. So this is the same thing as asking sine of x equals 1/2, right? I can flip both sides and make it easier to interpret. So sine of x equals 1/2, that's going to be in that pi over 6 family. So pi over 6 and 5 pi over 6. Cosecant of x equals -1, that's the same thing as flipping both sides and making it sine of x equals -1. And sine of x equals -1 when x equals 3 pi over 2. Okay. Yeah, these are the ones I'll have you guys try on your own. And let's go to number 5 here. Write the equation of each line in point slope form. We know how to do this, right? We can point slope form is y minus y sub 1 equals m times x minus x sub 1. If you have the slope in order pair, you can plug that in. If you're just given 2 points, you can do slope formula, get that slope, and then put into point slope form. So I'll leave that for you guys to try on your own. Let's look at part C and part D where we're not given everything to begin with, like A and B. So part C, we still want to write our equation in point slope form, but it says given the point -1, -2, so that's nice. We already have the point, but we want something that is perpendicular to the line y minus 2 equals 3 times x plus 1. So the only thing that we care about pulling from this second set of information is we just want to find the slope. We just want to use this to find the slope of the line that we want to build. So the only thing we care about from this whole second set of data perpendicular to this line, we just want to find the slope that's associated with the line that we want, and then do point slope form from there. Okay, so let's look at this here. What is the slope of this line? Y minus 2 equals 3 times x plus 1. 3, yeah, slope is 3, right? This is basically in point slope form. The slope is the number in front of the x. So that's the slope of this line, but the slope that we want is a slope that is what to this? Perpendicular. So what is the slope that's perpendicular to 3? Yeah, so it's the opposite reciprocal. We have to flip the number and we got to change the sign. So -1/3. Okay, so this is what we want. That's all we care about from this second portion is all we care about from this is just the slope. Get to the slope. So then the point is -1, -2. Our slope that we want to use is -1/3, and now we can put in the point slope form. And then just leave it in that point slope form. Part D, same process. We have the point, but now we want a slope that is parallel to this line. Now this line is a little bit harder in terms of it's not quite in the form where it's easy to pick out the slope. So why don't we just solve for y, and then we can have an easier time picking out what the slope is. Okay, divide everything by 2. So I've rewritten it in slope-intercept form to make it easier for me to pick out the slope. What is the slope of this line here? Just what? -3/2, right? Now, do we want to keep the slope or do we change it? Keep it, yeah. So it says parallel to this slope. So we want the slope that's exact same as this one. So we can use this slope and this point, and then we can do point slope form. Okay, next page. Okay, page 15, I think, these are all following the same process here. Find the equation in slope-intercept form. It says slope-intercept form. Let's just do it in point slope form. I think it's just. Okay, ultimately, it's it's up to you. I'm just gonna say, let's just do point slope form because it's, that's the form that we wanna get really comfortable with. But if you did slope intercept form, that wouldn't be wrong either. So we're gonna just take 2 points, find the slope, and then use either points to put it into point slope form, right? So all these you can just do slope formula to get to the slope. So that's pretty straightforward. Write the equation line that is parallel and normal. So normal means perpendicular. So similar process as what we did with the previous page. You take the equation that they give you. The only thing that you care from that line is get to the slope. And then once you get to the slope, you can build a slope that is parallel, which is the same slope, and then build one that is perpendicular to it. And then you can write the equations of the lines separately. So let me just do A with you, and then you guys can try B and C on your own. So here, the only thing we care about from this x plus y equals 4 is to figure out what the slope is. So I'm going to solve for y. So the slope is just -1, right? It's always the coefficient in front of your variable x, that's your slope. So then part A, we want to find a line that is parallel. Parallel just means use the same slope as the one that you found. So we take our slope, we take our point, and we do point slope form. So that's a line that's parallel to this line. Now we want a line that's perpendicular to the line, which means we have to adjust the slope, right? So now what's opposite reciprocal to -1? Just 1, right? So if I flip -1, I still get -1. And if I change the sign, I get from -1 to 1. So using the same point, I'm just going to do opposite reciprocal and keep everything else the same. Okay, I'll leave 8 and 9 for you guys to try. Let's go to page 16. Okay, we're going to practice condensing using log properties. So we have a couple of properties here. This is from page 12 here. So we're going to apply these properties here. We have 3 properties. You got power property, you have product property, and you have quotient property. And they can apply for logs of other bases as well. Let me just write them out here. So if we want to condense and write as a single log, what we want to do is we want to push all the coefficients up as exponents. So here, log base 4 of 3, we can't do much there, but we can do something with that 5. We can push that 5 up as an exponent. And now we can merge this using product property. So we're going to basically start on the right side and move to the left. So log base 4 of A plus log base 4 of B equals log base 4 of A times B. So this becomes log base 4, 3x. If I see a minus sign in between, then I'm just going to do quotient property. Now for part C, if you have multiple things going on, Let me kind of show you a little bit of a shortcut here. Well, first, we want to push all the coefficients up. And when we condense, we just want to produce one natural log expression. And ultimately, we just have to find a home for these terms here. We got to find a home for the 2, the x to the 4th, the y cubed, the 8th, and it's all going to land somewhere inside this log expression. So I think the easiest way to do this without having to, do multiple combinations and simplifying is just look to see what are these part of a positive or a negative log? If something is part of a positive log, then it's going to land in the numerator. If something is part of a negative log, it's going to end up in the denominator. So that makes it a little bit easier to just quickly see where each of these values belong. So the 2 and the x to the 4th, where can I put these? Numerator, okay. And the y cubed and the 8, we'll just put them denominator. Don't have to worry about, wait, I got to carry the negative over. The negative is taken care of with the denominator. Basically, the negative is it's going to force it in the denominator. So we're not going to worry about, having to change, having to add negatives. We're just, the negatives is basically going to put your expression in the denominator, and the positive will put it in the numerator. Okay. And we can try that with B and D later. Likewise, if I want to expand my log expression, I'm going to look at every one of my terms here and then just decide where they belong. Okay, if something is part of a numerator, then it'll be part of a positive log. If a term is in the denominator, then it'll be part of a negative log. So if we expand, we want all the pluses and minuses to show up. So here I have one term in the numerator, 2 terms in the denominator. So my expansion will just be a positive followed by 2 negatives. So log of x cubed minus log of 9 minus log of y squared. And then when we expand, we also want to push all the exponents down. So the 3, we also want to push it down in front as a coefficient. The 9, there's nothing here, we leave alone. And here the 2 we can bring down. Okay, questions? Okay, let's see. Page 17 and 18, I have the key attached directly for those on the back. Yeah, page 17 is just more writing equations of lines. So you guys can try that later. I do want to talk about page 18, number 6, finding the value for each of the following functions. We talked about how we can make substitutions. Right now, we don't really know what this represents, and we'll talk about this in the next unit. But for now, we're just going to practice with the algebraic portion of things. Okay. So here it says find the value of f of x plus h minus f of x for each of the following functions. Okay. So the goal is to basically try to get the numerators out of function notation. So there is an easy substitution here. What can I replace f of x with for part A? Just 3x plus 7, right? That's the easy substitution. The harder substitution is figuring out what can I put in place of f of x plus h. Okay. So this is the way that I want us to do it is if we know where that x plus h is going to go, then that's the hard part, right? Figuring out where that x plus h goes within the function. So I want you to write out the function with a reserved spot for all your arguments. So basically, wherever the x is in your function, go ahead and leave an empty space. So if you can take this step, you're not going to make a mistake because it'll be obvious where your x plus h goes. So now I've removed all the x's, and in place of it, I've put a reserved spot for any argument that I want to do besides x. So now, if I want to find f of x plus h, I'm just going to replace those empty spots with x plus h. Does that make sense? If it was f of 2, you would put f of 2 in here. If it was f of 5, you'll put 5 in here. If it was f of x squared plus 5x plus 3, you'll just replace all that empty space with whatever argument that you're trying to build. So now we have a substitution that we can put in place of f of x plus h. So now this will go in place of that. And then this will go in place of that. We're just getting the numerators out of function notation, but this is the harder piece to do, which is step 2. I think the natural tendency is some students see this and they say, oh, I'm just going to add the h at the end. So they say 3x plus 7 plus h, but that's not quite how it works. Okay, we have to make sure that we put the x plus h wherever the x is and not just attach the h to our expression. So I have x plus h, 3 parentheses, x plus h plus 7. So that is in the numerator. Minus, now what should we do after this minus sign here? Parentheses, right? Otherwise, we're going to forget to distribute through the parentheses all over h. Okay, we're just going to clean this up. This is going to represent something when we talk about 2 units from now. But right now, we're just doing the algebraic parts of it. Okay, so 3x plus 3h plus 7 minus 3x minus 7 all over h. Combine like terms, the x's cancel out, the 7's cancel out. I'm just left with 3h over h, and that reduces to be just 3. Okay, can we try part B? So with part B, when you put everything, once you get your numerator out of function notation, then just leave it alone. You don't have to spend the time to expand everything out. But let's just see if that process makes sense for you. There's also a key on the next page that you can check, but I want to see how far you guys can get on your own first. The part B. First. Force parentheses where the x is, and once you see those parentheses there, then you can put the x plus h. Don't do x plus h, just rewrite this function without x's. And if you can get those x's to show up, then that gives you smart food as essential. Okay, try part C. Yeah, we could reduce a little further with part B, but right now I just want us to know how to get the numerators out of function notation. We can worry about the rest later. And same process with part C. Go ahead and rewrite the function with the x's removed. Then you'll know exactly where the x plus h goes. For part C, I do want to see if we can practice doing common denominators with that. So let's try that. I think you guys are setting it up well. Okay, are we all able to get to this point here? Right, we're just finding this is an easy replacement. This is always just going to be the original function. This is the one that takes a bit of work. We want to make sure that we put the x plus h in the right place. So now we want to clean this up. And the way we're going to clean this up is we're going to step to the side and actually try to merge this into one fraction. But if I want to subtract two fractions, I got to find common denominators first. So I'm going to take this and kind of step off to the side and figure out what is the common denominator that can merge those together. So we know that what is the common denominator for these separate fractions here? What's a denominator that's large enough that can handle both those denominators? Yes, Nick. I need something large enough that both can multiply into. Any idea? So we don't want to overthink it. We don't have to find anything that is common between those two. If they look different from each other, then we need both of them to create our common denominator, right? So our common denominator is both the x and the x plus h. Okay. We need something large enough And if they're different, then we include both of them as common denominators. So now we got to balance these fractions, right? So this was the old denominator for the first fraction. What is this old denominator missing compared to the new denominator? X. So I need to balance the numerator with a x. So I need to multiply the top by x. So these are the same things. I've just adapted it so that it can actually fit with a new denominator. This denominator is missing what compared to the new denominator? X plus h. So I need to balance the numerator with an x plus h. So now I can merge this all into one fraction. What happens here? Numerator can just reduce to just what? Yep, negative 6h. So now we're going to take this and put it back where our original numerator was. So these are the same things. It's just that this is going to be easier to clean up because now we've merged this fraction into one fraction. So back to our original fraction, just with the new adjusted. Okay, are we good so far? Now, this is still a complex fraction. We want to reduce this complex fraction here. So if I'm dividing by a fraction, that's the same thing as multiplying by what? Reciprocal. So I'm going to do this. I'm going to take this, instead of dividing by h, I'm going to multiply it by the reciprocal of h. What's the reciprocal of h? Yeah, so negative 6h over x times x plus h times the reciprocal, you said 1 over h. And now it's easier to pair up things that can cancel out, right? What can we reduce? H's. Okay, so for next 5 minutes or so, see if you guys can pick up where we left off, any of the problems that we left off on page 13, 14, and start working through them. And I'll come around, I'll answer any questions that you guys have. And so next 5 minutes to see how much more we can get done. Oh, just like combining my terms. So I replace that sine squared actually with 1 minus cosine in the hopes that I can get everything from the 1/5. And I just brought everything over to one side. Yeah, then that's the original. So cosine squared plus cosine squared is 2 cosine squared. The ones cancel out, so that just goes away. 2 cosine squared minus cosine squared. Very good at this point. Okay, so now I'm just thinking in terms of my factor. So I factor GCF out, which is cosine of x, which is equal to cosine x minus 1. Like just getting that equal to 0, that equal to 0, like there. I'm just putting it here, you can circle that. So cosine of x equal to 0, that's like power 2 and 3 power 2. That's 2c. And then the other one is cosine equal to 1/2. That's first and fourth quadrant. So that power of 3 factor. So power of 3. Yes, yeah, you can. That's fine. I attached the key for the last 2 pages, but the other pages, I didn't attach the key, but it's on my website. So over the weekend, I'll also send out a link to that Pepper key page where you can find the keys for all these problems. Yeah, bring that 5 up, and then I think you just use this 5.
It doesn't have to be.
Yeah, this one's it's a hidden base.
Yeah.
So you just need that small.
Oh, thank you.
Okay, a few minutes remaining. You guys can come up and get your phones. And I'm gonna take up your packet on Monday and we'll start our limit 1 on Monday.